All right. So with some of the some additional topics with this week's content, we'll continue on now with how we interpret our Lewis structures. So, for example, here we're given the Lewis structure for hydrogen cyanide, HCN. So we have H, two dots, C. We have three pairs of dots, then an N, and then one pair of dots. So this can sometimes be written as follows: H with a line to the carbon, and then we have three lines to the nitrogen. And then you may have the leftover dots on the right side. So it says to count the number of bonding pairs and the number of lone pairs around the carbon atom in this molecule. So we're focusing here the on the carbon. Okay, so the number of bonding pairs of electrons. So a pair means two. So this carbon is bonding with the hydrogen on the left with this pair, right? That's a bonding pair. And bonding pairs of electrons are going to be found between elements, right? So there's that set in green. And then on the other side, we'll see that there's one pair, another pair, and a third pair of electrons that it's being shared, or that is being shared between the carbon and the nitrogen on the right side. So this carbon here now is sharing four pairs of electrons. So the number of bonding pairs then would be four. There aren't any lone pairs around the carbon. Lone pairs would be pairs of electrons that are not involved in bonding, and there aren't any around the carbon. However, there is a lone pair of electrons around the nitrogen. These two here, right? That's not found between the nitrogen and another atom. So this then is called a lone pair of electrons, and it's not involved in bonding. Sometimes they're called non-bonding electrons for that exact reason. Okay, but the question is not asking us about the nitrogen. It's asking us just about the pairs of electrons around the carbon atom. All right, let's take a look at, jump down here to the relative bond polarity. Okay, so it's asking us to rank the bonding or the polarity between the hydrogen bromine bond, the hydrogen chlorine bond, and the hydrogen iodine bond, where one is the most polar and three is the least polar. So all of these three compounds have one thing in common, and that's the hydrogen. Okay, that's common to all of them. What's different is what the hydrogen is connected to. So the hydrogen is connected to the bromine, it's connected to a chlorine, and then it's connected to an iodine. All right. So the difference between these, the bromine, chlorine, iodine, are their electronegativities. Are going to be different between the Br, the Cl, and the I. Right? Electronegativities we often abbreviate as En. And you can think of electronegativity as simply the pull that an element has on shared or bonding electrons. So for instance, the bromine, this bromine here, how strongly is it pulling on these electrons? And that's a measure of its electronegativity. Similarly, the chlorine, how strongly is it pulling on those electrons? And then the iodine, how strongly is it pulling on those electrons? Now, that electronegativity is going to be different. And you don't need to memorize electronegativity values. You should, however, know the trend in the periodic table. So we're looking at chlorine, bromine, and iodine that are here. So they're in the same group, the same column. And the general trend for the elements that belong to the same column or group is as you go up the group, the electronegativity increases. Okay, where fluorine is the electronegative element on the periodic table. So this means that out of these three that we were just looking at, chlorine is going to be the most electronegative, and iodine is going to be the least electronegative. All right, so chlorine here, this is the most electronegative, and then iodine would be the least electronegative. So what does that mean then in terms of how the shared electrons are being shared? Well, if the higher the electronegativity, the stronger that the shared electrons are being pulled. So in the case of the HCl, these electrons that are being shared between the Cl and the H, they're actually being pulled towards the chlorine more than they are around the H, right? So this bond then is going to be a polar bond. Chlorine is more electronegative than all the others. So out of the three, this is going to be the most polar. And in the case of the iodine connected to the hydrogen, yes, the iodine is more electronegative than the H. However, it is less electronegative than the chlorine. So it is going to pull in the electrons, but maybe not as strongly as the chlorine would. So this would be the least polar bond. And then in sort of intermediate would be the bromine hydrogen bond. All right, so that's how you want to interpret and navigate through that. You want to compare electronegativities. The more electronegative an element is, the strongly it's going to pull unshared electrons, which will make that bond more polar. The lower the electronegativity, compared to the other elements, the less polar the bond is going to be. All right, the other question looks at the intermolecular forces that are going to be acting between molecules of each of the compounds listed. And here we're going to now put several things into practice. So let's take a look at maybe the carbon dioxide first as an example. So the CO2. And we first of all need to draw the Lewis structure for this. All of these types of problems here will depend on you coming up with the Lewis structures first. So the first thing we need to do is to decide how many valence electrons we're working with. So we have one carbon, we have two oxygens. Valence electrons are the outermost electrons. We can quickly determine those by looking up the group numbers. Carbon is in group 4, so it's got 4 valence electrons. Oxygen is in group 6, so it has 6 valence electrons. So you have one carbon with 4. We have two oxygens with 6. So that gives 12, plus the 4 from the carbon gives 16 valence electrons. So my Lewis structure then, when I draw it, should have 16 electrons. We need to decide how these atoms are going to be arranged. As a general rule of thumb, if you see carbon in a formula, stick it in the middle, and the oxygens are going to be on the outside. We're going to connect the atoms to each other with a bond, which is just a line to begin with, so they don't float away. The next step would be to give the peripheral or the outer atoms enough electrons to complete their octet if they need it. So the oxygen on the left right now has 2 electrons that it's sharing. In order to complete its octet, it needs 6 more, so we put them in as pairs of electrons. The oxygen on the right is in the same boat. It needs 6 more electrons as well to complete its octet. So if I take a quick count of my electrons, I have 2, 4, 6, 8, 10, 12, 14, 16. Those are my 16 valence electrons. So I cannot put any more electrons into this structure. I need to make sure that everything has their octet. We've already made sure that the oxygens are happy with 8. However, the carbon in the middle, right, has 2 on the left and 2 on the right. So it's only got 4 electrons right now. It needs 8. So when your central atom is electron deficient, we can move pairs of electrons in to make multiple bonds. So if I move, for example, that pair of electrons in from the left, I can make a double bond between the carbon and the oxygen on the left. So the carbon is happier now than it was before. It's because now it has 6, but it needs 8, right? So it needs 2 more. I can move a pair of electrons in from the right side. And when I do that, I've created now a double bond on the right side as well. Okay, now my carbon has a total of 2 and 2, 4, 6, 8 electrons around it. The oxygen already had that 8, and we have 16 electrons. That will be my Lewis structure for, for CO2 carbon dioxide. So you want to make sure you draw in your lone pairs as well. I could have moved any pair of electrons around the oxygen, not just the ones that I put in. Okay, so we have our Lewis structure. The next thing we need to decide is the shape of this molecule. Okay, so the shape is all relative to the central atom, which is the carbon. The carbon here has 2 electron groups around it. So the double bond here counts as 1 electron group. The double bond here counts as another electron group. So it's got 2 electron groups around it. And in order for those electron groups to be as far apart from each other as possible, and that's the whole basis of the VSEPR, Vesper theory, in order for 2 things to be as far apart from each other as possible, that shape is going to be a straight line or linear. So the shape of this is actually the exact shape that we drew for the Lewis structure. That's going to look like that. Okay, the shape is important because when we look now at the intermolecular forces, we need to decide which ones are going to be present. And we have 3 options. We have dispersion forces, dipole-dipole forces, and hydrogen bonding. So right off the bat, all substances will have dispersion forces, which are the weakest intermolecular forces. We need to decide whether they're going to be dipole-dipole forces and whether they're going to be hydrogen bonding as well. So we can maybe eliminate hydrogen bonding, right? Because for a very specific reason, and it's in the name. In order for hydrogen bonding to be present, you need hydrogen, right? So guess what? There's no hydrogens. So then there couldn't be hydrogen bonding. So far we've decided dispersion forces because everything has dispersion forces. No hydrogen bonding. So we need to decide now whether they're going to be dipole-dipole forces. Okay, and in order for dipole-dipole forces, the molecule needs to be polar. So the molecule as a whole needs to be polar. Okay, so in order to decide that, I need to look up my electronegativity values for the elements involved in this. So we're going to look up our electronegativity values. So for carbon is probably one of the more common elements. And again, you need to look these up in your text. Okay, you don't have to memorize these. If you need it for a quiz or an exam, you'll get the electronegativity values. Carbon is 2.5, and then our oxygens are 3.5. So remember, the higher the electronegativity, the stronger that element is going to be pulling on shared electrons. So to the left of the carbon and the oxygen here on the left side, this oxygen on the left is going to be pulling on those shared electrons that way. So that's a polar bond. But guess what? On the other side, on the right side, we have the same thing happening, where the electron on the oxygen on the right is pulling that way, right? So these polar bonds are also called dipoles, bond dipoles. And in this case, we see that the overall molecule has these two bond dipoles. The question you need to ask yourself is, do they cancel out? And how do they cancel out? Well, they cancel out if they're equal and opposite. And the answer is yes, they are equal and they are opposite. So because now, even though your CO2 is made up of polar bonds, the polar bonds actually cancel each other out. So the molecule as a whole, so overall then, because the individual bond dipoles cancel, the molecule then is going to be nonpolar. And if it's nonpolar, then there aren't going to be dipole-dipole forces because there isn't an overall net dipole. So then the only intermolecular force of attraction that we have is going to be dispersion forces, right? We've just established why there isn't any dipole-dipole forces. So you want to go through these options. You want to come up with your Lewis structures, determine the shape, go through the bond dipoles, if any, and then decide based on the shape whether they can cancel. If they do cancel out, then the molecule is nonpolar. If they don't cancel out, then the molecule is going to be polar, and you will have your dipole-dipole forces of attraction. All right, and just to backtrack a little bit now on the matter elements versus compounds. Part of this week's topics. So in this question, you had to decide whether the sketches represent examples of a pure element or a compound. Okay, so just to talk about the differences here, an element, we have only one type of atom, okay, present in the sample. A compound, okay, we're going to have different elements present that are combined in a fixed ratio. So for example, if you take a look at substance A, right, the different colors represent different elements. So obviously now you have red and you have white. So you have different elements. So it couldn't be, or different atoms, sorry. So it couldn't be an element, okay? So the question is it a compound? Well, in order to answer that, those atoms need to be combined in a fixed ratio. So for each of these combinations, you'll see that there's one red and two whites, one red and two whites. So that means yes, substance A is going to be a compound. If you take a look at substance D, okay, so here you only see the red spheres, right? There's no other type of atom present, so there's only one type of atom present in this sample, so this has to be an element. If we jump down here now to changes that can occur, physical versus chemical changes. So in a physical change, okay, the identities of the substance stays the same. What may change is how the particles are arranged. Okay, that's a physical change. In a chemical change, the identity of the substance changes, and what that means typically is you have new combinations of atoms. All right, so if we take a look at our initial sample X that we have here, we'll see that there is two red spheres connected to the gray sphere in the middle, right? That's our original substance. That's a compound. If we look at what do we have? Look, change two, okay, what we'll see is that the identity is the same, right? So the compound is still made up of the two reds connected to the gray sphere in the middle, but there is a change that has happened. Let's see, we have the same number of particles, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have the same number of particles in change 2. The change that has occurred, though, is that the particles have become more organized, right? So here they're more sort of haphazard and random. In change 2, they've become more organized. It's a sort of a repeating pattern. So because the identity hasn't changed, okay, but the arrangement has changed, this would be a physical change that has occurred. So as you look at the other one, that's what you want to keep in mind, right? Does the identity change? If so, most likely it's a chemical change. If the identity doesn't change, but the particle arrangement has changed, that would be a physical change. You also want to pay close attention to see whether or not you have gained any atoms or lost any atoms, because that's impossible. Okay, you can't make stuff out of nothing. Okay, you can't make new atoms out of nothing, and you also cannot just destroy atoms. All right, that's impossible as well. So you need to count the atoms that you're starting with and make sure you have the same number of atoms that you end with. All right, and then the last couple of questions that look at energy and changes in physical state. So this question here um, asks you to convert different energy units. So for example, from calories to kilocals to kilojoules. Okay, and these conversions, the relationships between them are found in your textbook. So you want to look those conversions specifically between calories and joules. You want to find that in your text. The relationship between calories and kilocals, that's a metric conversion, right? That's going from kilo to something. So you should know that conversion. These are just math questions that you're doing, very similar to what we did in the previous week. In this diagram here, you're asked to interpret the graph, and this is a graph known as a heating curve, which shows the as you add heat on the x-axis, what happens to the temperature of the sample, right? That's what it's plotting in this on this heating curve. So as you go from left to right, you're adding a certain amount of heat, and then on the y-axis here, you're seeing the change in temperature. So typically, as you add heat, the temperature increases until you get to the point at which this physical state starts to change. All right, so we're starting off here with a solid down at the very beginning, and we're going to heat it. And as we heat it, the temperature of the solid increases till we get to the plateau, and the plateau represents a change in physical state going from the solid to the liquid. We keep adding heat until all of the solid has changed to the liquid, and then the temperature of the liquid starts to increase. We get to now the temperature at which the liquid changes to a gas, which is going to be the boiling point. We keep adding heat until all of the liquid is changed to a gas, and we get to the temperature at which or the point at which adding more heat now increases the temperature of the gas. So the boiling point is the point at which, or the temperature at which, the liquid turns into a gas, right? So you need to find that on that temperature that corresponds to on the graph. And then it says, what physical state of X would you expect to find in the flask after 10 kilojoules per mole of heat has been added? Okay, so that's just a unit here on the x-axis. So you find 10, which would be right here, and you follow it up in your graph, and you see where does it coincide with. All right, so the physical state that's present at 10 kilojoules. You know, the arrows here are all over the place. Let me pull that back out. So you want to start at the beginning, you know, going from the solid. The first plateau that you reach is going to be the solid turning into a liquid. And then the next portion would be the temperature of the liquid increasing. The second plateau that you get is going to be the boiling point.